guys, okay, today we are going to talk about section 3.3, the chain rule and the general power rule. So we talked about this in class, but just want to put a video out so that you can rewatch this if you need a little more help on it. So the general power rule, this is essentially going to be used when we have anything else other than just a plain old x raised to a power. So when the shortcut way to write this is n u to the n minus 1 u prime. So this would be something more like x plus 4 to the 5th. So do you see how this is more than just a plain old x raised to the power of 5? So with this, we're going to apply the power rule to this function. So if this is my y equals, y prime would be bringing that power in front. We leave the inside like it is, power minus 1 derivative of the inside. And simplify, we get 5 x plus 4 to the 4th. Okay, so anytime you see anything other than just a plain old x raised to a power, we apply this general power rule. So we're essentially hooking on the derivative of the inside to our power rule. All right, let's see some examples. All right, so this first example 1, f of x is x squared minus 3 all to the power of 2. So we're not able to apply the power rule because we have more than just an x raised to a power. So we're going to use the general power rule here. So f prime of x is bring your power down just like we do with the regular power rule. But here we leave the inside like it is, power minus 1, and then we take the derivative, or that hook-on factor, we take the derivative of the inside. When we simplify this, we'll get 4x times x squared minus 3. Now, it would be fine for you to leave it like this, or you could continue to simplify and say that's 4x cubed minus 12x. Now, we could get this same answer if we chose to actually multiply this out as x squared minus 3 times x squared minus 3, multiplied and then applied the power rule on each individual term. We would end up with this same answer. But using this general power rule is going to be a quicker way to do that. Here, algebra isn't going to be the quicker route. Let's look at example 2. So with example 2, we have g of x equals the square root of 2x squared minus x all cubed. So with this, we're going to simplify with a little bit of algebra first. This is 2x squared minus x all to the 3/2. So since I have more than just an x raised to a power, we're going to apply the general power rule. So with this, we pop our power down, leave the inside like it is, power minus 1, derivative of the inside. So this is our inside. So the derivative of 2x squared is 4x, minus the derivative of x is 1. So simplifying this, we get 3/2 2x squared minus x to the 1/2 times that hook-on factor of 4x minus 1. And this is simplified enough. I don't need to go into algebraically manipulating that anymore. Then we have there. All right, let's look at example number 3. So a couple of things going on here with example 3. Let's first rewrite this algebraically and see what we're actually working with. So this is 3x squared times 9 minus 4x squared raised to the 1/3. Now, since I have this power of 1/3, I'm not able to distribute the 3x squared inside those parentheses. So I have a product, and I also have more than just an x raised to this power. So we have a couple of rules going on here. We have our product rule, and within the product rule, we're going to have to use our general power rule. So if I want to find the derivative of this function, we're just going to write this out kind of the long way initially. So it is the first times by the derivative of the second. And I'm not actually taking this derivative yet. I'm just showing what I'm going to be doing. So we're taking the derivative of the second plus the second times the derivative of the first. So that's our power rule. So let's go ahead and take those derivatives. So we have our 3x squared. Now we're taking the derivative of this piece right here. Since I have more than just an x to a power, we have to apply the general power rule. So we're going to pop the 1/3 in front, leave the inside like it is, power minus 1, and then that hook-on factor of the derivative of this inside. So the derivative of 9 is 0, minus the derivative of 4x squared is 8x. So that's like a negative 8x. Plus the second times the derivative of the first. So the derivative of 3x squared is, this is going to have to squish in there, 6x. All right, so let's see what we can do to simplify this a little bit. These 3's can cancel, and we have our negative 8x here times by x squared. So that will give us a negative 8x cubed times by 9 minus 4x squared to the, I got a 3 there, that would be a negative 2/3. So that's this first piece, plus 6x times 9 minus 4x squared. Oops, let's see if I can, there we go, x squared to the 1/3. There's more algebraic simplification that can be done on that one, but it's not necessary. We can just leave that as our derivative. All right, moving on. So the chain rule is very similar to the general power rule, but we're just looking at essentially a composition of functions, so a function inside another function. So with this, we are taking the derivative of the outside function, we leave the inside function like it is, times by the derivative of the inside. So once again, that's the derivative of the outside function. We leave the inside like it is, times the derivative of the inside function. So let's take a look at some examples. Before we get to this one, let's just do an example from the homework that shows that chain rule just a little bit better. I'm going to pause this for a minute and grab an example for us real quickly. All right, so this is just an additional example. So let's say our function is y equals 5 over the square root of x plus 7. Now, as is, we would have to apply the quotient rule. So we know that the quotient rule is kind of one of the more lengthy rules that we have. So if we can algebraically manipulate this function to take the derivative in a different way, it's worth a try just to kind of see how that works out. So to get rid of the quotient, we want to move this from the denominator to the numerator. So this would be 5 times by x plus 7 to the negative 1/2. Now, this takes care of or gets rid of the fact that we had a quotient. Now, the question is, does it necessarily make this become a product rule? So the fact that this is just a plain old 5 without any variable attached to it makes it so we can treat this as a scalar multiple, which means we don't have to do the product rule here. Now, if I had a variable with that 5, then we would have to go ahead and apply the product rule. But we've taken this and changed it from a quotient rule to a simple chain rule, okay? So if I do the derivative of this function that we've algebraically simplified, 5 is just our scalar multiple. Now, the outside function is, it's like we had something all to the negative 1/2, so that negative 1/2 is like our outside function, and our composed function, or our g of x, is x plus 7. So if I do the derivative of the outside function, it's taking that negative 1/2, we leave the inside like it is, power minus 1, derivative of the inside. So this will simplify to negative 5/2 x plus 7 to the, if we get a common denominator here, that will give us a negative 3/2. You can leave this like this, or it can be simplified to 5 over 2 times x plus 7 to the positive 3/2. All right, so let's go ahead and look at this last example in our notes. So if P of 2 is 5, and Q of 2 is 3, and Q prime of 2 is 2, and P prime of 3 is 4, and Q prime of 3 is 3/2, find the derivative of P of Q of x evaluated at x equals 2. So this looks like there's quite a bit going on with this. Essentially what we are going to do is take the derivative of this generalized function, which is a composition. So we have Q of x inside of function P. So we're going to use the chain rule. So let's do this derivative in general, and then we'll apply all of these function values that are given to us. So the derivative of P of Q, whoops, undo that, Q of x. P is the outside function, Q of x is the inside function. So the chain rule says that we're going to take the derivative of the outside function, and we leave the inside function as is, times the derivative of the inside. So that's that kind of hook-on factor. So if I want to evaluate this at x equals 2, I would get P prime of Q of 2 times by Q. I keep wanting to do a G on that one, sorry. Q prime of 2. All right. So let's take a look at this. First of all, what is Q of 2? So if I look at my definitions, Q of 2 is equal to 3. So this is P prime of Q of 2 is 3. So I'm going to put a 3 in there, times by Q prime of 2. All right, so back to our definitions. Will this let me erase? Nice. Okay. P prime of 3 is given here, and that is 4. So I'm going to substitute 4 in for that value, times by Q prime of 2, which is right here. Q prime of 2 is the same as saying 2, which will simplify to 8. So on previous AP exams that I've seen, questions like this are frequently frequently asked. So they want to see that you can generalize a rule without having to take the derivative of like a specific function. They want to see that you know what the rule is and then apply values to it. So this will show up several times. You had it in the last homework. We've had a couple quiz questions similar to this. This is something that you definitely don't want to skip in the homework. And if you're having any troubles with it, please let me know and I'd love to help. All right, so I hope this helps with your homework for section 3.3, and I will see you guys soon. Have a good one.